Hi everyone, thank you so much for joining the video. Today's learning objectives are to firstly be able to calculate the rate of reaction and the half-life of a first order reaction using data from a concentration time or a volume time graph, and then to be able to deduce the order with respect to a substance in a rate equation using data from a concentration time graph or a rate concentration graph, and then to be able to deduce the order with respect to a substance in a rate equation using data from an initial rate method, and then to understand how to obtain data to calculate the order with respect to the reactants in the acid catalyzed iodination of these data to make predictions about species involved in the rate determining step, and to deduce a possible mechanism for the reaction. We're then going to look at a core practical, which is to do with rates of reaction, and it's going to be following the rate of the iodine propanone reaction by a tiotrometric method and investigating a clock reaction. We can actually find the order with respect to different reactants from initial rates data. And so as a recap, the definition of order of reaction is the power to which the concentration of the reactants is raised to in the rate equation. So the order with respect to each reagent can be found by doing a series of experiments where the initial concentration of each reagent is changed to see how it affects the initial rate. So if we imagine this reaction between T and U, so we've got T plus U goes to form products. So these are the experimental values that we found. And so how we work out the different orders is like this. So first I'm going to look at changing the concentration of T. So I'm going to select experiments 4 and 5 because it makes my life easier because the concentration of U stays the same. So we know that the difference in the initial rates for experiments 4 to 5 are only due to the different concentration of T. And so I like to draw an arrow. And what's happening here is that we're dividing the 1 by 2. So what's changed from experiment 4 to experiment 5 is that in experiment 5, we're using half the concentration of T. And what happens to the rate when we halve the concentration of T is that it also halves. And so this tells us that the order with respect to the concentration of T is 1 because when we halve the concentration of T, the initial rate halves. And we have the relationship of rate is directly proportional to the concentration of T to the power of n, where n is the order. So the order with respect to T is 1. And then now we have a look at changing the concentration of U. And so, as you can see, going from different experiments, there's no 2 experiments where we just change the concentration of U and don't change the concentration of T. So what we need to do is we need to use the information we've already got about T and use that along with working out the order with respect to U. So if I choose experiments 4 and 6, for T, what happens is that we multiply the concentration used in experiment 4 by 2. And then for U, we also multiply by 2. And then for the initial rate, we have multiplied by 8. So now we have a look at the concentration of T. So we worked out that the order with respect to T is 1. So if we multiply the concentration of T by 2, that means that the initial rate will also multiply by 2. And so that leaves us with times 4. And so what that means is that if we times the initial concentration of U by 2, then the initial rate we have found out multiplies by 4. And so this means that the order with respect to U is 2 because 2 squared is equal to 4, because it's not, the order isn't 1 because we're multiplying the concentration of U by 2. The initial rate isn't doubling as well, it's multiplying by 4. So that means that the order with respect to U is 4. And so now we can form a rate equation, and the rate equation would be rate equals k times t to the power of 1, and then u to the power of 2, and this will be our rate equation. And from this, we can also work out what the rate constant is, because we can do rate constant is the rate over the concentration of t multiplied by the concentration of u squared if we pick any one of these experiments, because the rate constant should always be the same as it's a constant. Now we're going to talk about concentration time graphs. So we could find the rate of reaction from a concentration time graph. We know how to do this already, and that's by finding the gradient. But we can also find the order with respect to a reactant by using these graphs as well. So the first one we're going to look at is if your graph goes straight down as a straight line like this. This indicates that it's a zero order with respect to that reactant. And then if we have a curve, then that indicates either a first order or a second order. And a first order would be a bit more smooth, whereas a second order would be a bit more steep. So this would be a first order with respect to that reactant, and then this one would be a second order with respect to that reactant. In a zero order reaction, the rate will actually be equal to k, and therefore the gradient of the line in a zero order reaction will give us the rate constant for the reaction, as well as the rate of reaction, because they'll be equal. And the way we can think about this is by using the idea of if we plotted a rate concentration graph. So we know that, for example, a rate equation could look like this. We could have rate equal to k multiplied by the concentration of A. Well, let's say, for example, we have a to the power of 0. So if we plotted that concentration rate against concentration graph, then what would happen we would get something like this, because no matter how we change the concentration of A, the rate remains the same. And so because the rate is equal to concentration over time, that means that the rate is equal to this gradient of this concentration time graph. And because this gradient is constant, that means that it's equivalent to this straight line rate concentration graph. And we can kind of apply that with the first order and the second order. So the first order, the graph would have a constant gradient, and then with the second order, the gradient would be increasing. Now I'm going to talk about half-life. So we can measure half-life from a concentration time graph, and we only need to do this for a first order reactant. So the definition of a half-life is the amount of time it takes for half of the reactant to be used up. So in this example, I have a reactant A, and we've plotted the concentration of A over the time. And as you can see, the half-life, so the time it takes for the concentration of A to half, so from 0.20 moles per decimeters cubed to 0.1 moles per decimeters cubed, that's taken us about 7 seconds reading from the graph. And the second half-life, it's the same. So we've taken, we've recorded the times that the concentration has decreased from 0.1 to 0.5 moles per decimeters cubed this time, because again, we're taking half of it. And that this is also 7 seconds. And so the really important thing to remember is that for a first order reaction, the half-life is always constant. And this is how we can tell between a first order reaction and a second order reaction, is that a second order reaction, the half-life will not be constant. Another type of graph that we can get is a rate concentration graph. And these kinds of graphs are much more useful, and we can see the order directly. So if we have a graph that looks like this, this is a zero order, because we know that from a rate equation, so for example, if we had rate equal to k multiplied by the concentration of A, if we have the concentration of A, the order of it, so the order with respect to A as 0, then that means we have rate equals K. And that means that no matter what concentration we have of this A, the rate won't change, because the only thing that determines the rate is the rate constant. And so that's why the gradient of this line is 0. And then if we have a graph that looks like this, then this is a first order. And we can see that by writing the rate equation out. So if we had this as a 1, instead of a 0, then we would have rate equals K multiplied by the concentration of A. And so that means that when we double A, we double the rate. When we triple A, we triple the rate. And so that's why the gradient is constant for this rate concentration graph. And then finally, for a second order, the graph would look like this. And then if we change this to a 2, well, if we double the concentration of A, then we quadruple the rate. And so that's why the gradient increases for this rate concentration graph. And these graphs can be produced from experimental data. So you can either use an initial rates method or a continuous rates method. So an initial rates method is when we do several experiments where the initial rate is measured and the initial concentration of a reagent is changed every time. And then a continuous rates method is when we do one experiment where the rate and concentration of a reagent is measured at several times during that one reaction. Now we're going to look at a required practical, and this is measuring the rate of reaction by an initial rates method. And so we're going to look at the reaction of iodide ions with hydrogen peroxide in acidic solution. And this is also known as the iodine clock experiment. So I'm just going to run through the method quickly. So first you use a pipette to transfer 10 centimeters cubed of hydrogen peroxide solution to a beaker. And then you use a measuring cylinder to transfer 25 centimeters cubed of sulfuric acid into the same beaker. And then using a burette, we measure 20 centimeters cubed of distilled water into a bigger beaker, so 250 centimeters cubed. And then we add a centimeters cubed of starch to this beaker, and then 5 centimeters cubed of sodium thiosulfate solution. We then stir the mixture and pour in the hydrogen peroxide sulfuric acid mixture and immediately start the timer. We then stir the mixture and stop timing when the mixture turns blue-black. And we repeat these steps, but with different volumes of the water and potassium iodide solution. So what's actually happening here is that the hydrogen peroxide reacts with the iodide ions to form iodine and thiosulfate ion. And we write this in the equation like this. So this is hydrogen peroxide, and this reacts with the iodide ions to form iodine and water. And then what happens is that the thiosulfate ion then immediately reacts with this iodine which has been formed. And so we have this second equation of this thiosulfate ion reacting with this iodine that's been formed by the first equation to form 2 iodide ions and this S4O6 2 minus ion. And so when the iodine is produced, has reacted with all of the thiosulfate ions present, excess iodine remains, and this remains in the solution. So then reaction with starch then forms the dark blue color that we see. So if we vary the concentration of I minus, we can determine the order of reaction with respect to I minus ions. So the rate equation for this reaction is actually like this. So you have rate and it's equal to K multiplied by the concentration of I minus to the power of m, and then multiplied by the concentration of the hydrogen peroxide multiplied by n. And so by varying the concentration of the iodide ion, we can determine its order, m. And the order with respect to iodide ions is found by varying its concentration whilst keeping everything else constant. So the rate equation therefore simplifies to rate equals k multiplied by I minus to the power of m. Or we can take logs, and this will make graphing it a bit easier. So we could have the log of the rate is equal to m times by the log of this concentration I plus a constant. So then now we can plot a graph of this. So if we say this is y, and then we have mx plus c, so that means that we're plotting a graph of log rate over log of the concentration of I minus. And so this m here, this will be the gradient, and this will also give us what the order with respect to I minus ions is. And the way we plot log of the rate is if we do log over 1 over the time, because rate is equal to 1 over time. So we plot log over 1 over time as the y-axis, and on the x-axis the total volume of each of the solution in each experiment is constant. So the concentration of I minus can be represented by the volume of the potassium iodide solution. And so we plot log of the volume of potassium iodide on this x-axis. And what we should get is we should get an order of 1. So the actual rate equation is rate equals k multiplied by the concentration of I minus to the power of 1. So we should get a straight line graph. So finding the gradient of this graph after we've plotted all our figures will give us the order with respect to those I minus ions. Now we're going to look at another required practical. So this required practical would be to do with the continuous rates method. So we're going to follow the rate of the iodine propionone reaction by a titometric method. And so what we do first is we add 25 centimeters cubed of sulfuric acid to 25 centimeters cubed of propanone in a beaker, and we mix that. And then we add 50 centimeters cubed of 0.02 moles per decimeters cubed iodine solution to the beaker and immediately start the timer. Using a pipette, we then remove a 10 centimeters cubed sample of the mixture to a conical flask and add a spatula of sodium hydrogen carbonate immediately to quench the reaction. What we mean by quenching is that we're stopping the reaction. And note that the time sodium hydrogen carbonate was added. We then withdraw samples every 3 minutes and repeat this process. With these samples, we titrate them with sodium thiosulfate using starch indicator. And so the indicator will turn from blue, black to colourless as the iodine reacts with the thiosulfate. So we repeat for all samples to find their concentrations. And we use these results to plot a graph of concentration over time. We also use a large excess of both propanone and sulfuric acid, and this is so that their concentrations remain effectively constant during the reaction. So this allows us to measure the influence of iodine alone on the rate of reaction. And so the graph that we get at the end is the concentration of iodine on the y-axis and the time on the x-axis. And then what we should get is we should get a straight line graph like this. And this tells us that it's a first order an order with respect to iodine of 1. So the rate equation at the end, you should get rate equals K multiplied by H plus ions multiplied by the propanone, so CH3COCH3, and this iodine. The order is 1, along with everything else. So this is the result that you should expect to get. And so from the experiment, because we've worked out the rate equation is rate equals K multiplied by the concentration of propanone multiplied by the concentration of H+. The H+ and the propanone must be in the slow step, so the rate determining step. And so the mechanism will contain a step with these two species forming a new species. And this is how we can predict the reaction mechanism. So this is actually an example of a proposed mechanism for the reaction. So we can see that there's a slow step of adding the H+ to the propanone because they're both included in the rate equation, so they both determine the rate. And then we've got fast steps until the end step where we have some more propanone being added, and so the last step is also slow. So now we're going to look at some questions. For the first question, deduce the rate equation and find the rate constant for this reaction from the following initial rates data. And so again, what we do first is we try and spot where one of them changes and the other one doesn't change to make it slightly easier. So we can see that from experiment 4 to 5, the concentration of E doesn't change. They use 0.1 moles per decimeters cubed for both of them. And so I'm going to pick experiment 4 and 5. So the concentration of D changes by a multiple of 4. And then the initial rate we see also changes by a multiple of 4. So that means that we've worked out that the order with respect to the concentration of D is 1, because if we multiply the concentration of D by 4, the initial rate also multiplies by 4. And so we have that the order with respect to D is equal to 1. And now we look at E. So there's no two experiments where the concentration of D is the same. So again, we're going to just have to pick something that looks kind of a bit easier. So I'm going to go with experiments 5 and 6. So D multiplies by 2, and the concentration of E also multiplies by 2, and the initial rate multiplies by 4. And so because of the concentration of D, and we multiplied that by 2, that means the initial rate of 20 in experiment 5, in experiment 5 should multiply by 2. So it should become 40. But it's multiplied by 2 as well. And we can see that the concentration of E has also multiplied by 2. And therefore, the order with respect to E is also equal to 1, because doubling the concentration of E has also doubled the initial rate from 40. So we have that the order with respect to E is equal to 1. So now we can form our rate equation. So our rate equation would be rate equals the rate constant times by the concentration of D to the power of 1 multiplied by the concentration of E to the power of 1. And so that's our rate equation. To find the rate constant, we then use one of these experiments and plug it into the formula with K as a subject. So we have K equals rate over the concentration of D multiplied by the concentration of E. So then K equals, so for example, I'm going to choose experiment 4. We would have 5 over 0.1 times by 0.1. So that would give me 500. And now we have to work out the units. So the rate is measured in moles per decimeters cubed per second. And both of these concentrations are measured in moles per decimeters cubed. And so now we can start cancelling stuff out. So I can cancel this moles per decimeters cubed out with one of these. And so we're left with seconds to the -1, and then moles to the -1, and decimeters cubed. So that's our answer.